Welcome back. In the previous lecture, we had introduced the notion of reaction cross-section in the context of nuclear reaction. In this lecture, we'll continue our discussion and introduce certain other features of nuclear reaction cross-section. There are two common ways of measuring the nuclear reaction cross-section. They are the reaction rate method and the beam attenuation method. Reaction rate method is used if the product is also radioactive, and its radioactivity can be measured. So here, for example, phi would refer to the intensity of neutron. We have already introduced this formula. In this context, phi would refer to the intensity of neutrons. The product is radioactive. How this experiment is done is the activity is measured after some time t, right? So AI is the activity after some time t. So during that time, the product would have decay. So this accounts for the decay of the product, that is the radioactivity of the product. And this is what you measure from, and this is known, this can be measured, and you know time, and you also should know the decay constant for that particular radioactive species. With all these things, it is possible to get sigma. Another method is called the beam attenuation method. Attenuation means decrease in intensity. This is very similar to what you may have seen in your high school regarding the Beer-Lambert's law, right? So in optical absorption, we use this. The decrease in intensity is of a particular, let's say, projectile is because of the collision between the target atoms and the projectile. Therefore, it is proportional to all these features, right? The distance through which the beam has traveled, reaction cross-section, target, and the intensity. So this decrease in intensity can be measured. And this formula is very, very similar to what you've seen in your Beer-Lambert's law of optical absorption. This is called the macroscopic cross-section. One place where this formula or this method is used is when there is more than one kind of nuclei which is reacting with the projectile. Okay, so N would refer to the sum of the different nuclei. So this is another method that is typically utilized. So there is another important feature. We will use this term. We'll revisit this term many times during the course of next few lectures. It's called excitation function. First, let's just look at some features. What is plotted here along the y-axis is the cross-section. The unit is bar. So for some different reactions, you're plotting how the cross-section changes with the energy of the projectile, right? So, for example, reaction 1, it's plotted here, refers to projectile proton reacting with copper nuclei, emitting neutrons and giving rise to zinc. Likewise, you can plot many of this. So here the energy of alpha particle is plotted, energy of protons are plotted here. What you generally see is the reaction cross-section increases to some extent and then decreases. This is very similar to, this form seems to be very similar to Maxwell-Boltzmann distribution, but this is a general feature. This work was published by a famous Indian nuclear physicist, Ghoshal. He worked with another very famous nuclear physicist, Emilio Segre. Segre got the Nobel Prize in nuclear physics. He was also the co-worker of Enrico Fermi. So Ghoshal has also written a very famous and very good book on nuclear physics. So in any way, this is one feature. We will understand these features later in the course of this course of these lectures. We'll move on to another feature. Here, the cross-section increases and decreases. In another context, in this context, the neutron is the projectile and silver is the reacting atom, nucleus. What you see are three particular features that are documented in this plot. First, there is this trend. As the energy of neutron increases, the reaction cross-section decreases. This is not intuitive at all. Then there is something called line width. Okay. So typically, let's say when you have a discrete spectrum, you may suddenly see there is an increase at a particular energy. Okay, so then that is called a line, but typically it is not a line. There is a broadness associated with that line. So it is called, this broadness is called line width. Okay, so what is the trend here? One trend is there seems to be a decrease in cross section, but another important feature is that there is a sudden increase in reaction cross section at certain energies, and there is a line width associated with these increase in cross section. Okay, these increase in cross section are attributed to resonances. In a way, this is similar to what you have seen in your classical mechanical scenarios. For example, you might have heard about increase in energy transfer at certain resonant frequencies, right? Supposing you have many tuning fork and you, let's say they're all planted on a wooden board, and then you, to this many tuning forks, you bring in another vibrating tuning fork. Okay, so the tuning fork would pick up this vibration is that which has a natural resonant frequency with the perturbing tuning fork, right? So what you typically refer to with references is enhanced efficiency in energy transfer. That is what is typically referred to as resonance in the classical context. That kind of notion is also valid here. So at certain particular energies, there is an enhanced energy transfer between the projectile and the reactant. And this enhanced energy transfer shows up as increased in reaction cross-section. And this reaction cross-section has certain width also. So the point I want to emphasize is this notion of resonances. Then there is also this spacing. This becomes closer and closer at increased energies, and the line width also decreases. These resonance transition becomes closely spaced, becomes bunched up, with the line width also becoming narrow. These four features are important. This decrease in cross section with increase in neutron energies, how line width changes, and the aspect of resonance and spacing. Okay, all these things give an idea of the underlying mechanism involved. Another important notion is to do with quantum mechanics. We started our discussion on reaction cross-section using notions from classical mechanics, right? There are two spherical objects colliding. We introduce reaction cross-section in this context. So as a first approximation, you would think that the reaction cross-section is of the order of the radius of the nucleus. But in some cases, the reaction cross-section is much, much larger than the projected area of the nucleus. For example, here we give some reactions. Again, the projectile is neutron. In these cases, the reaction cross-section, the measured reaction cross-section, cannot be rationalized just with the radius of the radius of boron nucleus and lithium nucleus. The reaction cross-section is much higher. To rationalize this, you have to introduce notions from quantum mechanics. So this lambda here is associated with the de Broglie wavelength. Okay, so this is a notion from quantum mechanics. So it is not sufficient to think about the radius of the nucleus alone. It is also important to think about the de Broglie wavelength of neutrons. All these things have to be introduced to rationalize the much larger reaction cross-section in certain scenarios. Again, we may look at this at a later point. In the next lecture, so with this, we complete our discussion on introduction to reaction cross-section. In the next lecture, we will take up an important mechanism for nuclear reaction. It is called the compound nuclear reaction theory. Thank you.